Hello everyone, we continue our course of formal languages, automata and codes, and today we shall have lecture number 13. This lecture you can find in my web page here, and the Ukraine version of this lecture you can find in my web page, coding automata and basic object algebraic theory, draft version, yeah. So we shall start. So our 13 lecture will be devoted to ideals in monoids. So we should start. Let M capital be a monoid. A right ideal of M is a non-empty subset R of M such that R multiply M is a subset of R. Or equivalently that for all R from R capital and all M from M capital will have Rm belongs to R capital. Since M is a monoid, then we have that R multiply M is equal R because M contains a natural element. Left ideal of M is a non-empty subset L of M such that M multiply L belongs to is a subset of L. A two-sided ideal, or also it's called an ideal, is an non-empty subset I capital of M such that the following condition holds: M multiply I multiply M is a subset of I capital. A two-sided ideal is therefore both a left and a right ideal. In particular, M capital in itself is an ideal of M capital. If the monoid M capital contains a zero, then the set which consists of 0 is a two-sided ideal which is contained in any ideal of M capital. An ideal I capital, respectively a left right ideal, is called minimal if J is a subset of I implies that J is equal I. For any ideal J of the monoid and respectively for any left or right ideal of monoid. If a monoid M capital contains a minimal two-sided ideal, then it is unique because any non-empty intersection of ideal is again an ideal. So I propose for you to prove this fact that the non-empty intersection of ideals is again in ideals. So as exercise 1 homework, good. If M capital contains a 0, then the set with the consists of 0 is a minimal two-sided ideal of M capital. An ideal I capital with distance from 0, respectively distance from left or right ideal, is called 0 minimal if J is a subset of I implies that J is equal 0 or J is equal I for any ideal J. So it's holds for any respectively left or right ideal. For any M element of M capital, the set R which is equal M small multiply M capital is a right ideal. It is the smallest right ideal containing the element M. In the same way, the set L capital is equal M capital multiply M small is smallest left idle containing element m, and the set I capital, which is equal m capital multiplying m capital, is the smallest two-sided ideal containing the element m small. We now define in a monoid m for every four equivalence relation R, L, J, and H in the following way. Two element m and m prime are equivalent if and only if the right ideals m and m capital is and m prime multiplying m capital coincide. Similar holds for left ideal. Two elements m and m prime are L equivalent if and only if these two left ideal coincides, and J equivalent if and only if two-sided ideal m capital m capital and m prime m capital coincide. Also, these two elements are H equivalent if and only if it's R equivalent and L equivalent, so this equivalent to the following condition. Therefore, we have, for instance, M is R capital M prime of if and only if there exists U and U prime from M capital, so that M prime is equal MU and M is equal M prime MU prime. Also, M is L equivalent M prime if and only if there exists U and U prime from M capital, so that M prime is equal UM and M is equal U prime M prime. Also, M is J equivalent M prime if and only if there exists U prime V prime from monoid M capital, so that M prime is equal UMV and M is equal U prime M prime V prime. So we have the following inclusion from this relation of equivalence. So R is a subset J and L is a subset J, and H is equal the intersection R and L. Proposition. Two equivalents R and L commute. So this means that we can consider the composition of the relation R and L, and this proposition says that the composition of these two relation commute. So prove. Let M and M are elements of the monoid M capital be such that M and N belongs to the relation R composition with L. So there exists P from M capital such that M R P and P L M. See in the following figure, yeah. There exists P such that there existed by definition U prime V prime from monoid M capital, so that P is equal mu MU and M is equal P U prime, N is equal V P, and P is equal V prime N. We put Q is equal V M. Then we have that Q is equal V M. Since M is equal P U prime, we put here, and gets the same, and V P is equal N, yeah, and hence we get the Q is equal N U, and similar N is equal Q U. This shows that element Q and N are equivalent. Furthermore, we have that mu is equal pu prime is equal v prime and u prime is equal v prime and u prime and is equal v prime q. Since q is equal vm, by definition of the element q, we get that q and m are L equivalent. Therefore, we get that m L equivalent q and q are equivalent are equivalent, and consequently we get that M and N belongs to the composition L and R. This proves this inclusion that the composition R and L is subset of the composition L and R. And the proof of the converse inclusion is symmetric, and this completes the proof of this proposition. Since the relation R and L compute, the relation D defined as a composition R and L is equivalence relation. We have the inclusion H belongs L, belongs D, belongs J, and A belongs R, belongs D and G. The class of relation D, called D classes, can be represented by a schema called X as an egg box as in the figure. The R class is represented by a row and L classes by columns. The square as the intersection of R class and L class are H classes. We denote by LM, RM, DM, HM, and JM, respectively, the L, R, D, H, and G classes of element M from monoid M capital. We have that H of M is equal R of M intersection L of M, and R of M and L of M is a subset of D of M. This is a subset of J of M. The next proposition, proposition 1.12.2, let M be a monoid, let M and N prime are element of M capital, B are equivalent. Let U and U prime are element of monoid M capital, such that M is equal M prime U prime and M prime is equal MU. The mapping row U, which puts elements Q U and P U prime, which puts elements Q prime U prime, are projection from the class of L equivalence of element M to the class of L equivalence of element N prime inverse to each other, which maps R classes into self. So this proposition in algebraic semigroup theory, well known so as first green lemmas. We shall prove this. The first, we verify that a row of U maps LM into LM prime. If Q belongs to LM, then M multiply MM capital multiply Q is equal M capital M, and therefore we get that M capital Q U is equal M capital M U is equal M capital M prime. Hence we get that QU is equal the image of element Q under the shift PU, and this element belongs to LM prime. Similarly, PU prime maps the class LM prime into class LM. Let Q belongs to the class LM and compute PU prime PU of Q. Since Q is L equivalent M, there exists element V and V prime from monoid M capital, so that Q is equal VM and M is equal V prime Q. See this figure is here. Since MU U prime is equal M prime U prime is equal M, we have that the image of Q under the map PU prime is equal Q U prime is equal VM U prime is equal VM is equal Q. This proves that the maps PU prime is the identity on the class LM. One shows in the same way that PU prime is the identity on the class LM prime. Finally, since Q U prime is equal Q for all Q of the class LM, the elements Q and PU of Q are is the same R class. This proves this proposition. The previous proposition has the following consequence, which justifies the regular shape of figure. This proposition states the following: any two H classes containing its same D classes have same cardinality. So this proposition states if you have some D class here, which is a union of L classes and R classes, and we can consider some square which is denote H class, that all two H classes in this D class have the same cardinality. Now we address the problem of locating all the idempotent in the ideal. The first result describes the H class of an idempotent. Proposition: let M capital be a monoid and let E is belong M be an idempotent. Then the H class of E is a group of units of the monoid E multiply M capital E group. Let M belongs to H class of idempotent E. Then we have that E is equal MU, M is equal E U prime, E is equal VM, M is equal V prime E for some elements U prime, V prime from the monoid M capital. Therefore, we get that EM is equal E multiply E U prime is equal E U prime is equal M. And in the same way, we get that M multiply E is equal M. This shows that M belongs to the following ideal E multiply M capital E. Since M multiply E U E is equal M U E is equal E, and E V E multiply M is equal E V M is equal E, the element M is both right and left invertible in the monoid M capital. Hence, element M belongs to the group of units of the monoid E M capital E. Conversely, if M is element of E M capital E is right and left invertible, we have that MU is equal VM is equal E for some elements U and V from monoid E M capital E. Since M is equal EM is equal ME, we obtain that M and E are H equivalent. This completes the proof of the proposition 112.4. The next proposition. Proposition 112.5. An H class of monoid M capital is a group if and only if it contains an idempotent. The proof. Let H be an H class of the monoid M capital. If H contains an idempotent E, then we get that H is equal H class, coincide with H class of idempotent E is a group by previous proposition. The converse statement is trivial, yeah? This completes our proof. The next proposition. Let M capital be a monoid and let M and M are element of M capital. Then the product M and N is in R intersection of class Rm and Lm if and only if Rn intersection of with Lm contains an idempotent. The proof. If the intersection of Rm and Lm contains an idempotent I, E, then we have that E is equal Nu, N is equal EU prime, E is equal Vm, and M is equal V prime E for some elements U prime, V prime from the monoid M capital. Hence we get M and U is equal M and M multiply NU is equal M E is equal V prime E multiply E is equal V prime E is equal M. So that we get that Mn and as element Mn and element M are equivalent. We show in some ways that Mn is L equivalent element M. Thus we get that N belongs to the intersection of the classes Rm and Ln. Conversely, if the element Mn belongs to the intersection of the classes Rm and Ln, then we get elements Mn and M are equivalent, and N is L equivalent to Mn. By proposition 112.2, the multiplication of the right by element N is an projection from the class Lm onto the class Lm N. Since N belongs to the class Lmn, this implies the instances of E from the class Lm such that En is equal N. Since the multiplication by N preserve R classes, we have additionally that E belongs to the R class of N, Rn, yeah, Rn. Hence, there exists U, an element of the monoid M capital, so that E is equal Nu. Conversely, Nu multiple Nu is equal E, Nu is equal Nu, and E is equal Nu is idempotent in the intersection of R class of N and L class of N. This completes the proof. The next proposition. Proposition 112.7. Let M capital be a monoid and let D be a D class of the monoid M capital. Then the following conditions are equivalent. D contains an idempotent, each R class of D contains an idempotent, each L class of D contains an idempotent. So this always that only one implies two require proof, yeah, and simple it is a simple application that from the statement 2 and from the statement 3 we get statement 1. Yeah, let E belongs to D, be an idempotent. Let R be an R class of D. The R class H sorry, this must be the H class. H is equal LE intersection R is in a non-empty here. It's right. It must be the H class here. Sorry. It is non-empty. Let N be an element of H. See figure Z. Since elements N and E are equivalent, there exist elements V prime from M capital such that N is equal VE and E is equal V prime N. Let M is equal E V prime, then we get Mn is equal E because Mn is equal E V prime multiply N is equal E multiply V prime N is equal V E is equal E. Moreover, if we have M and E are equivalent because Mn is equal E and M is equal E V prime. Therefore, we get that E is equal Mn is an element of the intersection of classes RR, Rm, and Ln. This implies by proposition, previous proposition that R is equal Rn contains an idempotent. This completes the proof. A D class satisfying once the condition of the previous proposition is called regular. Proposition 1.12.8. Let M capital be monoid and let H be an H class of M capital. Then the following conditions are equivalent. There exist H and H prime from H from H capital such that H prime belongs to H capital, and the second H is a group. The proof. First, we prove that statement number 1 implies the statement number 2. Yeah, if H prime belongs to H, then by proposition 1.12.6, the set H contains an idempotent. By proposition 1.12.5 is a group. The implication 2 implies 1 is obvious. This completes the proof. We now study the minimal and zero minimal ideals in a monoid. Recall that if the monoid M contains a minimal ideal, it is unique. However, it may contain several zero minimal ideals. Let M be a monoid contains a zero. We say that M capital is prime if for any M n from M without 0 there exists element U from M capital such that MU n is not equal to 0. Proposition. Let M capital be a prime monoid, then the following condition holds. First, if M contains a zero minimal ideal, then it is unique. If M contains a zero minimal right, respectively left ideal, then M contains a zero minimal ideal. This ideal is the union of all zero minimal right, respectively left ideals of the monoid M capital. If M capital both contain zero minimal right ideal and a zero minimal left ideal, the zero minimal ideal is composed of the regular D classes and 0. The proof. First, let I capital and J capital be two zero minimal ideals of the monoid M. Let M belongs to I capital without 0, and let N belongs to J capital without 0. Since the monoid M capital is prime, there exists element U from M capital such that MUN is not equal 0. Then MUN belongs to J capital implies that I capital intersects with J capital is not equal 0. Since the set the intersection I capital with J capital is an ideal, we obtain that I intersection with J is equal I is equal J. Second, let R be zero minimal right ideal. First, we show that if all M belongs to M capital A, the MR is equal 0, or the set MR is a zero minimal right ideal. In fact, MR is clearly a right ideal. Suppose that R capital is not equal 0, and let R prime is not equal 0 be a right ideal contained in the ideal R capital. We set S consists from such element of R that R belongs R prime. Then R primes is equal S capital, and S capital is not equal 0 because R capital prime is not equal 0. Moreover, S capital is a right ideal because R prime is a right ideal. Since S capital is a subset of R capital, the fact that R capital is a zero minimal right ideal implies the equality S capital is equal R capital. This shows that MR capital is equal R capital prime, and consequently that the set MR capital is a zero minimal right ideal. Let I capital be the union of all zero minimal right ideals. It is a right ideals, and by the preceding discussion, it is also a left ideals. Let J capital is not equal 0 be an ideal of M capital. Then for any zero minimal right ideal R capital of the monoid M capital, we have that R capital multiply J capital is a subset of the intersection R capital with J capital, and this is a subset of the R capital. We have that R capital multiply J capital is not equal 0, since for any R from R capital without 0 and M in J capital without 0, there exists an element U from the monoid M capital such that RUM is not equal 0, whence RUM belongs to R capital multiplied J capital without 0. Since R capital is a zero minimal right ideal, and the intersection R capital and J capital is a right ideal distinct from the 0 as an ideal, we have that the intersection R capital and J capital is equal R. Therefore, we get that R capital is a subset of J capital. This shows that I capital is a subset of J capital. Hence, I capital contained in any non-zero ideal of the monoid M capital, and therefore is the zero minimal ideal of the monoid M capital. The set, we shall next we prove the set statement. Let I capital be the zero minimal ideal of the monoid M capital. Let M and N are element of the ideal I capital without 0. By the previous statements, the right ideal M capital and the left ideal M capital N are zero minimal. Since the monoid m capital is prime, there exists element u from m such that un is not equal 0. The right ideal m capital being 0 minimal, we have that m capital is equal m capital. Therefore, element m is are equivalent to the element mun. In the same way, we get that element mum is L equivalent to element n. It follows that element m is D equivalent to element n. This shows that the set I capital without 0 is contained in D class. Conversely, if m is element of I capital without 0, n is element of monoid m capital, and element m and n are D equivalent, then there exists an element k from m capital such that m capital is equal k m capital, and m capital k is equal m capital n. Consequently, we get that I capital is equal m capital multiply m capital is equal m capital multiply k multiply m capital is equal m capital multiply n multiply m capital, and this implies that n belongs to ideal I capital without 0. Let us show that the set I capital without 0 is a regular D class. By proposition 1.12.7, it is in order to prove that the set I capital without 0 contains an idempotent. Let m and n are element I capital without 0. Since the monoid m capital is prime, there exists element u of m capital such that mun is not equal 0. Since right ideal m capital is 0 minimal, and since mun is not equal 0, we have that m capital is equal mu m capital is equal mun n capital. Thus, we get that mun belongs to our class of the element m. Symmetrically, since the set mn is 0 minimal left ideal, we have get we have that m capital N is equal m capital UN is equal m capital M UN. Hence, mun belongs to L class of element n. Therefore, we get that mun belongs to the intersection of the R class of element n and L class of element n, and by proposition 1.12.6, this implies that R the intersection of R class of element n and L class of element m contains an idempotent. This idempotent belongs to the D class of element n, and therefore belongs to the set I capital without 0. This completes the proof of the last sentence. So, as a consequence of previous proposition, we get the corollary 1.12.10. Let m capital be a prime monoid if m capital contains 0 minimal right ideal and 0 minimal left ideal, then monoid m capital contains a unique 0 minimal ideal I capital, which is a union of all the 0 minimal right respectively left ideals. This ideal is composed with a regular D class and 0. Moreover, we have the following computation rules. So, for all elements from I capital without 0 and n belongs to m capital such that n is not equal to 0 or 0, we have that elements m and mn are equivalent. Similar, we have that element m and nm are L equivalent, and for any H class H which belongs to I capital without 0, we have that A square is equal H, or A square is equal 0. The proof. The first group of statement is an easy consequence of the proposition 1, 12, 9. Let us prove statement 1. We have that mn multiply m capital is a subset m capital. Since the set m capital is 0 minimal right ideal and mn is not equal 0, this forces the equality m capital is equal m capital. The proof of the statement 2 is symmetric. Finally, to prove statement 3, let us suppose a square is not equal to 0. Let h prime element of H class H be such that h prime is not equal 0. Then by statement 1 and 2, we get that element H and H prime are equivalent, and H prime and H prime are L equivalent. Since H and H prime are L equivalent and H prime and H prime are L equivalent, we have that H is L equivalent to element H prime. Therefore, we get that H prime belongs to H capital, and H capital is a group by proposition 1, 12H. So this completes the proof of our corollary. Now we give the statement that corresponds to proposition 1, 12, 9 and corollary 1, 12, 10 for minimal ideal distance of 0 minimal ideals. This is of course of interest only in the case when the monoid does not contain a 0. Proposition: let m capital be a monoid, then the following condition holds. If monoid m capital contains a minimal right respectively left ideal, then m capital contains a minimal ideal which is the union of all the minimal right respectively left ideals. If the monoid m capital contains a minimal right ideal and a minimal left ideal, its minimal ideal I capital is a D class. All the H classes in the ideal I capital are groups. The proof: let 0 be an element that does not belongs to the monoid m capital, and let m0 is equal m capital united with 0 be a monoid whose law extends that m of m in such way that 0 is the 0 of m0. Yeah, the monoid m0 is prime and ideal. It is obvious. Yeah, because the product of all elements of monoid m belongs to monoid m. Yeah, and hence there are no elements distant from 0 from m0, so that the product is equal 0. An ideal I capital, respectively a right ideal R or a left ideal L capital of the monoid M capital, is minimal if and only if the union I capital with 0, respectively the union R with 0 and the union L capital with 0 is a 0 minimal ideal, respectively right ideal, left ideal of the monoid M0. Moreover, the restriction to M capital of the relation R capital L capital D H in M0 coincide with the corresponding relation in M capital. I propose you to show that in monoid M0 the following condition holds. Exercise 2. Good. He continues. And therefore, statement 1 and statement 2 can be deduced from proposition 1, 12, 9 and corollary 1, 12, 10. This completed the proof of the proposition 1, 12, 11. Okay? And we get the following corollary. Let M capital be monoid containing a minimal right ideal and a minimal left ideal. Then monoid M capital contains a minimal ideal, which is the union of all minimal right respectable left ideals. This ideal is a D class and all its H classes are groups. So we finish our lecture. Thank you for your attention. I wish you health. I wish you good luck and goodbye.